Hello, everybody. Hope you're enjoying the Chromium University so far. This talk is going to be a little bit different. I'm Peter Norvig. I'm a director for research at Google, focusing on artificial intelligence and machine learning. I joined Google in 2001 as the first director of machine learning. And at the time, I told them sometime this is going to be important to the company. And I probably underestimated how important. Uh, this talk will probably be a little bit different than some of the other ones you're hearing today, which are more focused on technical details. This one we're trying to give you basically an overview, more of a big picture. And to do that, we're going to have to go through a history. And let's go all the way back to the pre-industrial era. In the 19th century, work was hard. There was scant automation and tools, and people did everything by hand. Then, in the first half of the 20th century, work was powered by workers like this using machines like this. So we're starting to use automation to get work done. The second half of the 20th century was powered by computers. Here's a couple of iconic examples. On the left, that's Margaret Hamilton standing next to the flight software for the Apollo missions that she helped develop. And it turns out she was actually my first boss on my very first job out of college. So that was a lot of fun for me. On the right, very young Paul Allen and Bill Gates. In the 21st century, let's call that the information age. The computers got much bigger and big data ruled. And here we have a data center far beyond what we could have imagined of the computers of just a few decades before. And then finally, we turn to color like in The Wizard of Oz, and we have the machine learning age. Most recently, that means that the widespread deployment of machine learning that made the data more useful. Of course, we've had all these ideas of artificial intelligence and machine learning going back to Alan Turing in the 1950s, but it's really the impact on the average citizen that's changed and it's coming to the forefront just in the last decade or so. Okay, so that's the big picture. Now let's get into some of the details. We're talking about a history of AI. I came into the field in the 1980s. It had been going on for a couple decades. And when I entered, it was really the pre-industrial era. You had to do everything with your own hands, and that mostly meant the blood, sweat, and tears of grad students like me. So everything we wanted the computer to do in an intelligent way, we had to write down step by step. And it was logic-based. We were writing things whenever X and Y are true, then Z is true. And to some extent, that looks like a regular programming language, where in programming language, we say if X and Y, then Z. It was a little bit more abstract because I'm saying whenever rather than if. So programming languages have this idea of flow of control. You're in one place at one time. AI had the idea of let's abstract that away. But it was still pretty close to a programming language, and debugging was hard. We also had the idea that, up to now, there was this notion that computers were all about numbers, but we wanted a field that was about thinking. And so that probably meant it had to be non-numeric. And we wanted to be able to deal with representations of structures that didn't have to do just with numbers. And that was a good idea, but I think we took it too far. And the notion of the time was what we called an expert system, where we would go out and interview a domain expert, an expert, say, in chemistry or in space exploration or in medicine. And then we would duplicate her reasoning processes by writing down these kinds of knowledge step by step, if A, then B, and so on. Now, we soon came to a shift. I have it down as the 1990s. For in the academic domain, it really started in the 80s, but didn't deploy until the 90s. And the first important part of the shift, due largely to Udaya Pearl from UCLA, was a shift from a logical approach to a probabilistic approach. So rather than say whenever X and Y, then Z, we say what's the probability of Z given that X and Y are true? And that gave us a much better capability to deal with uncertainty and allowed us to go into fields that we really couldn't do before, things like self-driving cars, where everything is uncertain. We also shifted from an expert system approach to a normative approach, where rather than say, this is how the expert do it, say, this is what is true. So it's not how to do it, but just what the facts are. And we shifted to this optimizing approach, saying, given what is true, let's try to do the right thing. Let's try to get the result that optimizes some objective measure. So it made the whole field a lot more scientific. Then the most recent advance was to look at more data and think of it as data coming in as at sort of low level rather than the high level knowledge. And that the high level knowledge would come from emergent representations. So rather than having to have a grad student write down everything they know, we learn from reading text, and we interpret words as vectors, not as atomic symbols. We combine them together, and those emergent representations, the words combine into sentences, the sentences combine into paragraphs, those combine into ideas. That's where we ended up where we are today. It's hierarchical. We chose to use this word deep, as in deep learning, and all that means is that one level of representation leads into the next level. Now, Mark Andreessen is famous for saying software is eating the world, and now it may seem like machine learning is eating software. And maybe we're going to change everything about how we write software. And it will no longer be programmers saying, if X, then Y. It'll be feeding in the right kind of data and then having the systems automatically optimize themselves. That looks like the direction we're heading. How far along are we? How long is it going to take to get there? Those are the big questions. Now, the field of programming as a whole has had 50 years of tool building for traditional programming, but we've really only had a few years of serious tool buildings for machine learning. Here's some of the types of tools we have in our kit today. But if we're changing this whole idea of how software is written, rather than telling the computer step by step what to do, we're now changing it to collect data, build a model, and have the system optimize itself. It feels like we're going to need some new tools, and we aren't quite there yet. Now, I'm old enough to remember when this was a state-of-the-art programming tool. So you took out a pencil and you traced through those little templates and you made a flowchart. That's where we were when I started programming. And it feels like we're almost that primitive when it comes to tools for doing machine learning. We just don't have the tool set yet. And it probably shouldn't be surprising. It took us 50 years to figure out how to do regular programming well. And machine learning programming is probably more complicated. So it's going to take a while to get the tool set right. And we're on that track. We've got a long way to go. Okay, so what is the standard machine learning model? Well, in the easiest case, we start off with some labeled data. So we have a collection of photos with labels associated with them. This is a cat. Then we do some deep learning, we download TensorFlow, and we do some magic, and then profit somehow magically occurs. So that's the standard model, but of course, that's naive and incomplete. And the real model is much more complex. So here's a more realistic model consisting of 8 different steps, and I won't go through them one by one. That would be an entire separate talk and another hour. But note that there's several steps around collecting and managing data. And then in the middle, there's this core machine learning model, and then several more steps around deploying the model. Now, I spent a lot of time talking to startup companies, and when we show them this type of approach, they're always scared about this step number 5, evaluate and debug and modify your machine learning model. And they say, this looks complex, it's got a lot of math in it, with the Greek letters and so on. I know this is going to be the hard part. And they imagine that where the bubbles here are proportional to the size and the effort they have to put in, they imagine that most of the effort is going to go into debugging those machine learning models. But inevitably, across the board, once they start to build these systems, they find out that it's really pretty much the opposite, that most of the effort is up front in dealing with the data, getting the right data you need and transforming it in the way you want. Machine learning part is the easiest part. And then the second hardest part is deploying it and keeping the system up and running. So what is it about that machine learning part that makes it easier than expected? Well, I think a big part of it is that it's differentiable. And that's a fancy word that just means that when the output you get at the end is not what you expected, you can feed back the error and minimize the error step by step all the way back to the beginning. So it's self-correcting. If you have enough data coming in, the model can correct itself. And that's not the whole story. There's certainly lots of parts to it. I'm not saying that it's completely automatic there, although we're trying to build tools to make it more automated. But the self-correcting part, I think, is crucial to making it easier than expected by the naive users. Now, part of the problem, though, is that it's only differentiable, it's only self-correcting within the model itself. And what we would really like is something that's self-correcting throughout the whole process, but we don't have that yet. And so what happens is teams are making choices in the early steps, 1, 2, 3, 4, which is the data collection and curation. And those steps might be the optimal steps at the time, but when the world changes and the data changes, now those were no longer the right choices. And since the model is not completely differentiable end to end, a human has to notice that and go back and revisit those decisions. I would like to see a machine learning in the future where all of that is automated, where you look at what are the decisions you could make. If you make the wrong one, the system notices and goes back and optimizes that for you. And so I think that's another place where we need the right tools to do that. Okay, so everything I've said so far has been pretty abstract. Now I want to get into some examples to give you a better idea of what can be done with machine learning. And I'll just go through some of the projects that I've been involved with a little bit or have worked with or know about. Here is a great project by some physicists at Stanford who were looking at the problem of gravitational lensing. So what does that mean? So that means we're here on Earth, and someplace far away there's a galaxy which is sending light towards Earth, and in between there's another galaxy which is bending that light. And if we could figure out how much it spent, then we could learn something about those two galaxies, about their weight and about the presence of dark matter and so on. But turns out it's a really complicated mathematical problem to figure that out. And the way the physicists had been doing it is they were saying, let's guess about what that galaxy far away is, then let's run the calculations that can be done according to physics, and that will tell us what the light is like on Earth. And if it doesn't match what we actually observe in our telescope, then we'll make another guess and we'll continue. And it took using supercomputers over months to make enough guesses to get that right. What these physicists said is, I don't know anything about machine learning, but I heard about this TensorFlow stuff and these deep networks, and I understand that what they do is work backwards. And that's really exactly what I want to do in this situation. I don't want to go forward from the light coming from the galaxy to the light showing up on Earth. I want to go backwards from the light showing up on Earth that I actually observe to what the galaxy must be like. It sounds like these deep learning networks do exactly that. And that was right. And so they went from knowing nothing about machine learning in a couple of weeks to having an answer that gets the right answer and does it 10 million times faster. So that's a great example of a success, very technical domain. And of course, physicists are very technical experts. Normal people, when you start throwing around words like tensor, they get a little nervous. Physicists eat that for breakfast, so that's no problem for them. Another similar example of space explorations. So I used to work down the road from Google at the NASA Ames Research Center, and we had a project hunting for exoplanets, planets around other suns. And one of the ways to detect them is to look for eclipses, where the planet passes in front of the distant star and brightness goes down, and we can say that's an eclipse, and we can measure how big that planet is. It only works, eclipses are rare as we see them here on Earth, but if you're looking at millions of stars at once, then they're pretty common. And sort of traditional statistical approaches had looked at the data coming in and had found all the good examples of eclipses of a really big planet, a Jupiter-sized planet that was close to the sun and eclipsing a large part of that sun. Those were easy to find. But we were able to go back with using these machine learning techniques and find other examples that were harder to find, to differentiate between what's an eclipse and what's something else. Maybe it's just some fluctuation in the amount of dust between you and the target. So we were able to extract more from the data that we could never do before. There's a lot of applications in medicine. Here's one at looking at images of the retina and diagnosing disease there. And machine learning vision systems can do that better than doctors can do it. Here's two examples of high school students that I've had the pleasure to be able to work with. Both have worked on separate projects having to do with identifying cancer. It's not only disease in people. Here's another project having to do with identifying disease in plants, in particular cassava plants. Why is this interesting? Well, it's just another example of disease prediction. So in some sense, that's not such a big deal. But the interesting part here is that it's out in the rainforest. So we can't put supercomputers out in the rainforest. We can't even put laptops out there. So it all has to do with running on mobile devices. And a big part of machine learning today is saying, how can we get these systems that we know how to run in the data center and squeeze them down so that they can fit in a mobile device and have low power. Another example of that is fighting illegal deforestation, also in the rainforest. You see Topher White there, putting up a system where there's a solar array to keep the batteries powered and an off-the-shelf cell phone. And what it's doing is its microphone is on and it's listening for the sounds of machines coming through, of buzzsaw, of chainsaws activating. And when it hears that sound, it locates where it is. If it's in an area where forestation is not allowed, then it communicates in a mesh network with the other cell phones and sends a signal back saying, hey, there's something going on here that shouldn't be going on. Here's the location. Come out and check it out. Auto captioning videos. So we've had a lot of success in speech recognition where you dictate sentences into your phone and it gets it right. You'd think that would be trivial in auto captioning videos, but it turns out it's not quite the same because there's a lot more going on in these videos, a lot of background noise, and also the captions aren't just what is the dialogue, but it's also those little parts in parentheses of saying, now there's a car crash, or now the character is walking away, and so on. So an application that's not quite off the shelf, that uses a lot of pre-built mechanism we have for speech recognition, but goes beyond that in a certain way. And I think that's where we are now, where a lot of machine learning applications are like that, where what you think was the hardest part, the core part, is already done, but then around the periphery, there's plenty left to do to make that machine learning application work. Another example of giving us an idea of where we are, this work is taking a science exam at the level of an 8th grader and being able to pass that. Now, it can't quite do everything. It's really much better at the multiple choice questions than at the more open-ended ones, but it gets them right. And these types of questions, it takes us, in order to understand that, it looks like it takes a degree of understanding that's well beyond the just parroting language back and forth. Here's another example. This is a company called Connectera. And every company's got to have an elevator pitch or a slogan that tells you what is a company like. And Connectera is we're a Fitbit, but for cows. Why would cows want a Fitbit? Not to boast on Instagram, but it gives the farmer an idea of here's this cow. Are they doing some? Do they look like they're sick? Are they drinking too much or too little? Are they walking too much or too little? And so this is a way for a farmer to manage their whole herd. And we've seen a lot of applications in farming and agriculture, looking at the health of trees and plants and so on. So branching out from the health for people to health of everything else. Okay, so AI has been meeting the real world. And I think that's really the message of the last few years. I've been in this field since the 80s, and I felt like a lot of my work was theoretical. We were happy about the advances we were making, but most of the time we were talking to our fellow researchers. And, if we wrote a paper and we got a couple hundred, or maybe if we're lucky, a couple thousand citations, we felt really good that we were able to reach thousands of people. But now we're at the point where we're meeting millions and potentially billions of people. So that's what's different. And when we do that, there's lots of societal questions that come into play. So one of the big questions we're hearing about is, what about jobs? Is automation going to take these jobs away? And we see headlines in papers like the New York Times questioning the role of automation as a job challenge. That's something that's new, but wait a minute, is it really all that new? Because actually this headline is from 1962. So this is when we first thought about automation as being a problem. Of course, then it wasn't machine learning, then it was just machinery, mostly farm machinery, but also assembly line type machinery. So this is the challenge that's been going on for a long time, but it's a big issue today. So these challenges of job displacement, challenges of privacy and security, challenges of fairness in society, these are all big issues that used to be peripheral, but now are at the core of what machine learning and artificial intelligence are doing. So I said we've had a shift where traditional programming talked about how should we do it step by step. And now we've moved more into a domain where instead we're saying, what should we want? So in a machine learning system now, you say, what is it you're trying to optimize? You collect a lot of data, and then the model automatically optimizes that. So we've come into a position where our technical challenge is being able to express what it is that we want. And then if we can do that, the rest is easy. You gather the data, you build the model, your problem's done. And so that sounds good. It sounds like an advance. But as a society, we've got a lot of warning signs. And we have legends around how difficult it is to say what it is we really want. So here's one of the best examples, the story of King Midas. He was asked for a software specification of what it is that he wants. And he said, well, what I want is for everything I touch to turn to gold. Unfortunately, he didn't run enough unit tests or integration tests. And this picture here is depicting all his food and his child turned to gold. So that's not what he really wanted. So he made a mistake. But there is technology, and there are guidelines where he could have done better. All right. So all King Midas had to say was, I want everything I touch to turn to gold, but I want an undo button in case I get something wrong. Right. And so we have mechanisms that we know about that can mitigate the problem of making a mistake in specifying what we want. And we need to do a better job of making those widespread, making them part of the common practice so that we don't get into these problems where what we said we want is so different from what it is that we actually want. So maybe we're getting rid of the programmer or minimizing the role of the programmer. We no longer have to say, here's where we go step by step. Uh, here's how we get from A to B by saying if this, then that. And maybe instead, we need somebody to tell us, figure out what it is that we want, figure out how to get us going in the right direction. And is that going to be a teacher, somebody who teaches the system how to achieve what it wants by example? So certainly a lot of machine learning is based on showing examples, and maybe the role of a teacher is right for that. Or is it a philosopher? Philosophers are the ones who deal with the questions of what is it that we really want. So I think there's something to that. So I consulted a philosopher, Mick Jagger here, who's well known for his writings on the subjects of what it is that we want. He said something along the lines of, you can't always get what you want, but you get what you need. And so that's an interesting statement, but unfortunately, with respect to where we are now in machine learning and in technology as general, I think Mick actually got it exactly wrong. Because these are the things that we need today, but we've built this system to allow us to say what we want by clicking away and swiping in our browsers and our phone. And our feedback says these are the things that we said that we wanted. And they don't necessarily align with what we really need. Because of the way that the system is written, we have this marketplace for attention, and the competitors in that marketplace have figured out how to give us things that will allow them to take our attention, but they aren't necessarily focused on what we need. The marketplace sort of runs itself, and the competition means we're guided away from the things that we truly need towards these things that we said we wanted in the short run. So, I can go and I can play this game for hours at a time. And then at the end, I can say, oh man, that was stupid. Why did I spend my time doing that? I wish I had those hours back. But it's too late. Of course, I don't have a time machine. I can't get my hours back. But it's even worse than that, because every click I make is also a recommendation to this system. And so my weakness in succumbing to playing this game that I thought I wanted, but I didn't really want and I didn't need, turns out to be a recommendation to everybody else. And so it spreads like a virus, and they end up doing it too. So going forward, what we would like to put in place is something that protects us against that focuses the marketplace back towards what we really need and away from these superficial things that's easy to say what we want. And so I think those kinds of questions are going to be a challenge for the future. Yeah, as a machine learning researcher, there's all sorts of technical questions that are really exciting right now and that we can do a better job. But overall, the big challenge for us is going to be at the societal level, not at the technical level. And that's where I see us focusing attention in the coming years. And I wanted to stop now and throw it open for discussion, since there's so many big issues that I tried to cover here, and I'm not sure what you guys are really interested in. So I wanted to leave plenty of time to open it up and talk what you guys want to talk about. Okay. So number one on Slido, Sam Goto is asking, GPT-3 seems really impressive. Any thoughts on whether it's a substantial step from where we are or just an incremental one? So great question. I think it is a big step because it does stuff that we've never seen before. But I'm not sure it's what the right conclusion is exactly about what it's a step for. To me, one of the big lessons is, well, maybe language processing is less impressive than we thought it was, right? We thought that this was the one thing, right? So a lot of people have said the thing that distinguishes humans from all other animals is this ability to use language. Yeah, other animals have some kinds of signs. They do communicate to each other in certain ways, but nobody uses language the way humans do. And we felt like everything that's going on in understanding involves a deep level of intelligence. What GPT-3 might be saying is maybe that's not necessarily true, that maybe a lot of language use is just parroting things back. And if you look at the movie Being There, Peter Sellers plays this character who does not have a complete understanding of everything that's going on in the world, but he dresses nicely and he uses the right words, and everyone projects onto those words a deep understanding, right? So his character is a gardener who is falsely interpreted as being a diplomat, and they ask him, "What do you think about the economic situation?" And he says, "Well, we need to plant the seeds in order for the garden to grow." And everyone interprets that as a metaphor about the economy, but it wasn't. And I think that's a lot of what's happening with GPT-3 is we get an answer back, and we like to throw onto it more understanding than it actually has. And some things it gets right, and other things it gets wrong. I did a talk the other day where I was at a university virtually, and I showed them, well, let's try real time to write the brochure for your university. And so it took the two-sentence mission statement off the university's website, fed that into GPT-3, and it came back with a two-page brochure, and it was kind of right on. It said sort of all the things that you'd expect to see in a university brochure, and it looked pretty promising, except the last couple lines, and the university president was there, and she was not too happy with the last couple lines because it said tuition $1,203, right? So it definitely had some lack of understanding. It could throw words and symbols together, and it kind of knew that a number should come next after tuition, but I had no idea what the right number should be. And I think that's a lot of what's happening with GPT-3. Now, how could we get beyond that? Well, so the limits of GPT-3 is all it has as input is text, and we have a model of the world behind that, but it only has that model to the degree that the text has correlations with each other. I kind of believe that to get to the next level, I would like to not just throw in more text, which is one of the things that's been done, or throw in more parameters to the model, make the model bigger, which is another thing that's been done with some good success. I think we need to go beyond that. And I think one promising approach is a multimodal model. So instead of saying, let's cram more text into one of these language models, let's say, let's combine a text model with an image model and a video model, right? So if I really want to understand, in images, we started off by saying, here's some pictures of cats. If I really want to understand what's going on with cats, I don't want to just have more pictures. I don't want to just have more text that have the word cat in it. I want to combine the pictures and the text and the videos. And now I have a better idea of what cats are actually doing when I can actually see them moving around. So I think that'll be the next step. So come back in a couple of years and we'll have this discussion again, where there'll be these larger multimodal models that are doing interesting stuff. And then we'll again have the same discussion of how deep are they actually understanding what's going on, and how much is it just a surface correlation with data that they've seen in the past. Okay. Let's see. Neural networks seem to be performing comparably or better than handwritten algorithms. Where does it ever end? Right. So that's pretty interesting, and the things you mentioned here are, each of them is different in a certain way. So physics simulation, why was the machine learning model doing better? And there, I think the answer was because it had this ability to go backwards. So it wasn't doing better in the sense of getting a better prediction, because in physics, we have really good models of what the physics is like, right? We've got these rules of F equals ma and so on. And for the most part, the real world actually follows those rules. So in physics, the problem was just how can we arrive at the right solution faster? How can we search the space of the solution? And the key there was going backwards rather than going forward. And this idea of differentiating to eliminate the error, that was the right approach. So in some sense, it wasn't even really a machine learning approach. If deep neural networks did not exist, a physicist could have come up with that solution without inventing all this mechanism that we have for machine learning. So that's one type of answer. Sorting, in a way, I think is similar, right? So sorting, and so for those of you who don't know, for things like sorting, for things like allocating memory, we've had a lot of success with machine learning algorithms that learn to do better than the hand-coded algorithms. And how can they do that? Well, so in one sense, you can't do better, right? So we know if you're trying to do sorting and you're allowed to do comparisons, in the worst case, you can't do better than order n log n. But what turns out is nobody cares about the worst case. They care about my case. And in the real world, the data you get is not completely random. It's not completely adversarial. Rather, it comes from your users in a certain way. And what machine learning allows you to do is learn an algorithm that takes advantage of that, that doesn't say, I want to be able to sort any sequence coming in. Rather, it says, I want to do a better job at sorting the sequences that I'm actually seeing. And in some cases, we've seen humans have been able to do that, to understand the distribution of the particular data they have and write an algorithm. But machine learning seems to be better at picking out those patterns. And then let's see, what was the third? Protein folding. That's, I think, is something that's just really hard to think in 3 dimensions. And so I think that's why machine learning does better. So in each of these cases, there's a kind of different reasons why the machine learning algorithms are dominating. Where does it ever end? I think we'll see more and more of this, where handwritten algorithms will be replaced by machine learned ones. And I think we're already seeing this kind of flexibility, right? So, even things as that seem as cut and dry as like operating systems and compilers, we're moving towards a world of more flexibility. And we saw this even without machine learning, right? So this idea of doing compilers that are just in time rather than pre-compiling everything ahead of time, that's been around without the emphasis of machine learning, and that's a successful approach. Machine learning allows you to do that kind of thing even better. You can do best just-in-time compiling with some statistics for how you think things are going to come out. So I think here machine learning is really just saying, if I understand how the problem I'm dealing with is different than the abstract problem, how the data I have is constrained to some types of inputs, but not other types of inputs, then machine learning is what you want. And I think we'll see more and more examples of that. Okay. What are your thoughts on the grand engineering challenge of reverse engineering the brain? How does that fit into the field of AI today or in the future? So that's a fascinating problem. I wrote a textbook on AI, and we took the explicit step of saying we're going to define that as a separate field, right? So neurologists have their own field of understanding the brain, and that's certainly related and impinges on AI, but we're going to define that as separate. And the two can go their own way, and then they can also work together, and the feedback can go in both directions. I'm not that excited about reverse engineering the brain because I want to build systems that work, and sort of the hardware that I have is different than the brain. All right, so the capabilities of what a computer can do and what it's really good at is very different from what a brain is really good at. So, if I need to multiply two 10-digit numbers, I'd really rather use a computer than a brain. If I want to remember exactly all the words on 100 billion web pages, I'd rather have a computer than a brain. But there's lots of other things for which the brains are currently better at. So I think it's good that we're looking at the connections and trying to do the best. And a lot of what we've done in speech recognition and in computer vision has a lot of insights from the way that the brain works. But and I want to gain from those insights, but I don't want to be limited by them, right? So if part of my solution is I can just memorize 1 trillion facts, even though a brain can't do that, if my computer can do that, I want to allow my computer to do that. I don't want to limit it to only be reverse engineering what the brain is doing. So some things the brain is the right architecture for, some things it is limiting. And so that's the way I see it going. I think we'll understand the brain better. I think we'll understand some of the deeper mysteries of how it works, just in terms of doing tasks like vision and understanding language. And I think at some point we'll understand the deeper questions of, what is consciousness? Do we really have free will, and so on? But I think of those as separate questions for neurologists and philosophers, and I'm happy to focus on machine learning aspects, and I'm happy that there are other people focusing on those questions. Okay. Current AI applications seem to be focused and narrow. Any development on a society of AI algorithms, sorting out their incentives, reinforcing each other, et cetera. Yeah, so that's a really interesting problem, and I think that's right, and I think that's part of how engineering works. That we like to solve problems by breaking them down and into components, and so sort of the engineering discipline that we've had for hundreds of years has this approach of being focused and narrow. I like the idea of a society. Marvin Minsky had this idea of society of minds. I mentioned this idea of large multimodal models. And so I think that in the not too distant future, a lot of what we do will kind of work that way, right? So right now, most of the AI applications we have are bottom up. You start from nothing, you feed in the data you have, and you build kind of the smallest possible model that will solve that problem. That's the methodology we have today. I think in the future, it may be you go to one of the cloud providers, they have a gigantic model that has all the data they know about, and then you subtract from that model just the parts you need to solve the problem you have. So it's a narrowing down rather than a building up. And I think that may become a more common approach that will make it less focused in terms of solving the problem you want to solve. And then there's also this issue of the society. I think that's really interesting too. And one of the things I've been following is the rise of these assistants, the Google assistants, the Siri, the Alexa, and so on. And they're interesting in their own right as kind of machine learning systems, as speech recognition systems, but they're also interesting from the point of view of operating systems. And it's really only like once a generation that we get to change the whole paradigm. We went from mainframe computers to personal computers, to mobile computers. And maybe these assistants is another one of the revolutions on that scale, where it's not just the form factor of the device. So, if you had asked me 6 years ago, do you want to give away your mouse and your keyboard and your screen and just have a speaker that you talk to? I'd say, what, are you crazy? Why would I want that? Why would I want to give up all this good stuff? But it turns out I was wrong, and people do want that to some degree. So they like that form factor. But it's more than the form factor. It's also the way the whole operating system is written, right? So today, if you look at on my phone, if I want to get something done, I press one of these icons, and now my phone is completely taken over by Pizza Hut or Lyft or whatever company I've pressed the button for. And they're in control of the UI, they're in control of the communication, and they guide me towards solving this goal that I wanted to have, of having a pizza show up or whatever. With the assistants, it's not like that. We have some capability for these companies to interact with the assistant, to write actions and responses and so on. But it's still, I'm talking to the assistant first, and then all the companies are kind of bidding for my attention. So that's a big change in the way these operating systems are written. And I think it'll take a while before we realize, how much do people want that? I want it to some degree, and a lot of people have these speakers out there. I don't think anybody is completely giving up on their other devices and having this device only. It's more a factor of when is it the right time to use them. But this is going to be a big change if things go this way. It may be very helpful in terms of privacy and security, because right now, a lot of people are a little bit wary, right? So you download a new app for your phone, and the screen comes up and say, do you have permission to do the following things? And nobody reads that screen. They just press OK. And then if it seems a little shaky, they delete the app later. But if you were talking directly to your assistant, and then it had a society of apps and companies on the side that were kind of bidding for your attention, you may feel more secure. You may feel like you had something that was on your side rather than everybody else bidding for your attention. And that would be a shift in the way we interact. And so I think that's really interesting. So we'll see over time how much that plays out. Okay. Where are we in neural network, human explainability, interpretability? Is that a solvable problem or a fatal flaw? So I think that is a big issue. And explainability, interpretability are two big words that are thrown about. To me, they're just part of the problem. And to me, the sort of top level word should be trustworthiness. Do I trust this system? And I was just talking about, maybe I can trust my assistant more if I feel it's on my side rather than trust the apps, which I kind of know belong to somebody else, and maybe they're not on my side. So trustworthiness is the main goal, and there's lots of ways of getting there. And certainly explainability and interpretability are part of that, right? So you want to have, if I say, you just said this, why should I believe you? You want to have an answer. But I think part of the problems with explanations is they're kind of after the fact, and an explanation is just a story. It's not sort of a proof, and everybody's got an explanation. So, you look at any type of prediction for what's the weather going to be tomorrow, who's going to win the football game, who's going to win the election, is the stock market going to go up or down? Everybody's got a story beforehand of what they predict is going to happen, and that story is an explanation. This is going to be the winner because of A, B, and C. But then after the fact, if they get it wrong, now they've got another explanation. And before the fact, everybody's got their own explanation, and they're different. And so we can't tell from an explanation whether it's correct or not. we can tell, we can often tell if we believe it's definitely wrong, that there's some flaw in the explanation, but oftentimes there's not. And I think explanations are different than the actual reasoning, right? So if I go to the doctor and say, what's wrong with me? And she says, I think it's this. And I say, give me an explanation. I think what's really going on is the doctor is relying on her decades of experience and kind of subconsciously coming up with an answer. And then when I ask for an explanation, now she kind of goes back to med school and picks out all the facts that support the answer that she had already come up with unconsciously or subconsciously, and kind of downplays all the stuff that goes against that. So an explanation is just a story, and how accurate that story is not 100% correlated with how meaningful it is, or how believable it is. It's possible to fool people with those stories. So I want explanations, but I want more than that. Another example is sometimes you really need statistics, not just explanations. So if I apply for a loan and I get turned down and I ask, give me an explanation, the explanation might be, oh, well, you didn't have enough collateral. How do I know that's the right explanation? How do I know they're not prejudiced against me because of my background in some way? Well, I can't tell just from their one explanation for me. But if I say, I don't want an explanation, I want to audit you and have a breakdown of who was approved and not approved, broken down by all these protected groups. Now I can say, oh, look, it looks like you have a history of prejudice against this particular group. And I can tell that from the statistics, but I can't tell it from just my one case. So I think there's a lot of tools that go towards trustworthiness. And these are really important. I don't think they're a fatal flaw, but I think we need to build them in. And, I've certainly seen that at Google. I've been around at the company for a long time, and, the old timers tell me it's so much harder to launch a project now because there's all these new reviews for privacy and security and fairness and stuff. And we never had that before. So there's some resistance towards getting that right, but I think it's crucial to get it right. And I think we, as a field, we should really change our expectations to say getting all these things right is just as important as having the system give the right answers and not crash. Let's see. If possible, could the development of a system of intuition, even emotion, expand the applicability of AI? What would an AI be capable of if it could play? Yeah, so that's interesting. I'm not sure exactly what that means, and certainly there have been notions of playing and exploration, and I think using words like play is maybe anthropomorphizing it a little bit too much, but this idea of not getting stuck in one place and being able to explore other alternatives. There have been lots of papers around how to do that, and I can give you details if you're interested. I do like this idea of separating out kind of the automated part from the intuition part. And so one of the examples I thought was really interesting is we have a project at Google around theorem proving, mathematical theorem proving. So you give me a statement of something in math that you want to prove, and it comes back with a long proof, step A, B, C, D, E, F, G. Now, in order to do that, you have to feed into the system a bunch of axioms of what you know is true. Arithmetic is associative and commutative, and so on and so on. So all those axioms are in the system, and then it can, there's a sort of non-machine learning system that can search for proof using those axioms. And in one sense, this is automatic and foolproof, right? So if the theorem is true, with an infinite amount of computation, the system would find the answer. The problem is we don't have an infinite amount of computation. And so if there's too many axioms, then the system can't find the answer. So we kind of broke this up into that technical part and then an intuition part, where up front we said we're going to use a neural network to say, here's the description of the problem. Now, what axioms do you think might be relevant? So it's what using your kind of intuition, put that words in quotes. What's your intuition as to what are the right axioms to solve this problem? And now do the technical part with that much more constrained, smaller set of axioms. And that system works much, much better. So that's a way, maybe it's cheating a little bit to call that intuition, but maybe it's not. Maybe that's the way real mathematicians think about it. Is they said, I just have a feeling that the proof is going to go in this direction. And the mathematician has these two skills, the intuition to make those calls up front, and then the technical skill of being able to grind out the answer. So let's see, where are we? Do we have time for one more? What sort of things could someone start doing now if they're interested in contributing to the advancement of AI? Is academic research, graduate education required? I think some kind of understanding of where the field is required. But there's lots of great online courses. I don't think you have to sign up to get a graduate degree in order to start contributing. So I would say start by going out and building something, right? And so look at an open source project, download something and play with it. Look at some data that you have that nobody else has that you're interested in doing something with, and build something with that. And then notice where you succeeded and where you failed. And if there's some part that you failed and maybe you came up with an answer to fix the problem, or maybe you haven't yet come up with an answer to fix the problem, look and see, are other people having the same kinds of issues, and can you contribute to that? So I would start by example and go from there, and that might lead to a paper, it might lead to building a new type of system. There's a lot of possibilities, and it doesn't have to be formal. A lot of what's going on now is going on in the companies because they are trying to build these real world systems. And interesting stuff is being done by independent researchers and by open source projects. So I think the field's wide open. Maybe 1 minute more. Okay. You said that we may need a societal shift to get things we need versus want, as opposed to a technical shift. How do you envision that taking place? Who drives it? Yeah, so that's a great question. And I think it's a mix. I think you're seeing companies being much more aware of these types of issues, right? So we're doing all these things with privacy and security, with federated learning so that your data belongs to you and so on. I think companies are recognizing that. I think governments are trying to step in and figure out what their role is. And so the role of like the GDPR in Europe has also made us rethink our privacy type issues. And I think there'll be a partnership there between governments and industry. And some of it may be consumers having to make choices, and I don't want to place everything on the consumer. It's not like, you have to strike or something. That's too much to ask. But, if there's a choice between two apps and one has better privacy than another, then maybe starting to make that choice and starting to be aware of those types of choices, that can also help drive things in the right direction. And I guess we're out of time. Thanks so much for the opportunity to be able to talk with you.